I think we're live. It's looking good. I think we're live, and with that, we're going to begin today's ESAHangout. Hello and welcome to the Rosetta mission hangout. ESAHangout focusing on the topic, how we arrive at a comet. My name is Daniel Scuka. I'm Senior Editor for Spacecraft Operations, and I'm here at ESAC, ESA's Mission Control Center in Germany, together with Rosetta Flight Director Andrea Accomazzo. Andrea, thanks for joining us.
Thank you, Daniel.
In STech, we're also joined by Fred Jansen. He's working at ESA's Technical Center in the Netherlands, and he is our Rosetta Mission Manager. Fred, also, thank you very much for joining our ESAHangout today.
Thank you, Daniel.
And we have a special guest, certainly the most distant one. We're joined by Padma Yanamandra-Fisher, an astronomer and physicist at Colorado Space Science Institute. She's logging in today from JPL, NASA's JPL, the Jet Propulsion Lab in California. Padma, thank you very much for getting up so incredibly early in the morning to join our ESAHangout.
Thank you, Daniel.
Just a quick note on Padma. She is actually one of the coordinators on the CIOC, the Coordinated Investigations of Comets. It's an international grouping of professional and non-professional astronomers and space scientists, and she's going to share with us today some of the latest news on the ground observation campaign looking at Comet 67P. In the first half of today's ESAHangout, I'll ask each of our guests to provide us an update from their particular areas, and in the second half, we'll actually answer as many of your questions as we can get to. We do invite you to send in your questions. You can send them via Twitter using the Ask Rosetta hashtag. You can also post them right here in the Google Plus channel. And our colleagues from the ESA social media team, Maria Bennett and Emily Baldwin, are working behind the scenes to scan through all of your questions, extract them and put them together, and I'll pick them up on a laptop here just to my side. So we hope we can actually get around to answering as many of those as we can. Right, without too much more, I'd like to get started, and I'd like to begin with Andrea. You're here at ESAC working on the working with the Rosetta Flight Control Team. And we're wondering if you can give us an update on mission progress so far since Wake Up in January, and how things are looking as we look forward to arrival at the Comet on the 6th of August.
6th of August. All right, thanks, Daniel. So first, yeah, we have spent the past month since hibernation exit in January in preparing ourselves for this Comet arrival. The spacecraft was already on an approach trajectory to the Comet. This approach would have been far too distant from the comet than what our scientists want to do, so we had to prepare it further. The first thing we did was to check out completely the spacecraft. This took a couple of weeks, and we found the spacecraft in an excellent status after the hibernation. Then we took care of checking out the full instrument complement, the scientific instruments on board the spacecraft. This took much longer. We spent 6 weeks full-time working on this issue. And the great news of this is that neither the spacecraft nor the instrument had suffered any damage throughout this almost 3 years hibernation. This was fantastic news for us. After this, we were in a position to start maneuvering towards the comet. And this is what we have started doing in May. Early May, we started performing some maneuvers to divert the trajectory of the spacecraft more into the direction of the comet. So we are on an approach trajectory that is getting closer and closer to the comet. What we are also doing is we are also changing the relative speed of the spacecraft with respect to the comet. So the two objects, we are traveling at the very beginning with 800 meters per second relative speed, and we are reducing this relative speed to almost zero. This is what we are doing these weeks. We had big concerns because these are big rendezvous maneuvers that we have to do with our onboard thrusters with the rockets. The biggest ones we have already completed, and they've worked extremely well. So the spacecraft is on its perfect approach trajectory towards the comet. We have slowed down the spacecraft significantly compared to the comet. So now we are entering the final phase of the approach phase. The more we get closer to the comet, the slower we are in approaching the comet. This is a strategy that we have developed. The comet is outside if we compare it to the sun and to the spacecraft, so we can happily take images of the comet, and these are absolutely needed in approaching the comet. So this is what we are doing these days. In the coming weeks, we will switch to a mode where we do approach maneuver every single week, and every time we reduce the relative speed and we reduce the distance to the comet. Up to the 6th of August, which is the time when we will really get to the comet. At that stage, we will start orbiting the comet from very close neighbors. We will start taking more detailed images. We will develop all the models we need to then really fly around the comet at low altitudes and be able to deliver the lander at a later stage.
I'm just going to zoom back out here and get back on the camera. Great, thank you, Andreas. Now, I'm just wondering, what does it look like when we arrive at the comet? What sort of orbits do we do around the comet? How do we actually stay close to it? Because I understand we actually don't have a very strong gravity once we first get there.
Yeah, that's correct. There are 3 things we have to do to be able to accomplish our scientific objectives too, which is rendezvous and orbit the comet. The first thing is to approach the comet, and this is, as I said, is what we are doing now. We had a big uncertainty on the position of the comet itself, and this we have to resolve, and we do it by taking navigation images. This process has been started. We have exercised something similar in the past when flying next to asteroids, and we are doing this. Once we get to the comet on the 6th of August, we have to face the fact that we know very little of the object we want to orbit and we want to characterize. We don't know the gravity potential. We have some estimations, but we don't know it. We don't know the attitude of this object. We don't know the rotational status of this object. We don't know the shape. We don't know anything. And if we want to orbit this object, then we have to resolve all these characteristics. So we initiate a characterization phase. In order to characterize the object, we need some reference points. We don't know, since we don't know anything of the comet, we have to determine what are our references. So the first thing we do when we approach the comet on the 6th of August, we create a catalog of what we call landmarks. These will be our reference points in determining the properties of the comet and in determining what the spacecraft is doing around the comet. Once we have characterized and have a catalog of these landmarks, then we can determine how they move in the images we are taking, so we can determine the rotational status of the comet. By seeing how the spacecraft moves around the comet, then we can also determine the gravity potential of the comet. We can also, with the images, reconstruct a 3D shape model of the comet. Once all this is done, then we are in a position to go down and really orbit the comet. And then the third challenge starts. The comet is an active object, is emitting gases, is emitting material. These gases, this material are impinging onto the surface of the spacecraft, and they're perturbing the trajectory of the spacecraft. And this is the biggest challenge we have from an operational point of view in flying around the comet.
Great. Andrea, we're here at ESAH. We're actually just a few meters over that way is the Rosetta dedicated control room, the DCR. Could you give us a little bit of flavor on what is daily life like here for the team right now? We've just finished, or we're just finishing this phase of orbital correction maneuvers where we're doing a burn every 2 weeks, and pretty soon we're going to start doing a burn every week. What's the pace of life and the pace of work here for the team?
Well, there was one beauty of this phase leading from the hibernation exit up to what we are doing now, that activities were ramping up slowly. So we started reactivating the spacecraft, reactivating the instruments, then we started maneuvering towards the comet. We were doing maneuvers every second week, and this gave us time to practice, to exercise our planning cycles, so the cycle that leads from designing the maneuver, computing the parameters, up to commanding the spacecraft on every second week. Now, as from next week, we will do this cycle every single week. And as from the 6th of August, we'll do it twice a week to command the spacecraft. So this was the beauty of this phase that allowed us to ramp up. What we are doing fundamentally is we are continuously now assessing the relative position of the spacecraft compared to the comet, use these parameters to design the next maneuver and program it. In parallel, some of the instruments are already performing scientific activities, so we are receiving inputs from the colleagues sitting in ESA, the Science Operations Center, that are collecting the inputs from the scientists, putting them together in a timeline for scientific operations, and we are also preparing the commands to operate the instruments for observations. The more we go into the mission, the more activities the more demanding from a timing point of view will be, the more tight, or the tighter will be our deadlines will be. And this, we are preparing ourselves for this challenging phase.
Good stuff. Thank you. I see there are already a couple of questions which probably will best go to Andrea. A couple of people are asking about the actual delta V that we have to achieve. You had mentioned about this approximately 800 meters per second to get up to the comet. Also about some of the landmarks on the comet that we'll be looking for. I'll put those on pause for right now. We're just into the first bit of our hangout today. I'd actually like to switch over to Fred Jansen in STech and get his update, and keep posting your questions. We'll gather them here and place them to our guests a little bit later on in the program. Fred, you're mission manager for Rosetta. It's actually one of the most exciting, challenging, and incredible missions ESA has done or is doing this year anyways. It's a pretty big job. What are the things that you have to do on a daily basis to keep the mission functioning and to keep all the people who are involved in the mission more or less coordinated?
Well, first of all, trying not to panic, and then on a more serious note, my job is about making sure that all the elements involved in Rosetta interact in the correct way, and that they're all able to do their work, so that all the infrastructure, all the support, everything is there. And that, I mean, you have mentioned now a few of the building blocks of Rosetta, which is the Mission Operations Center in Darmstadt at ESAHangout and the science operations in Spain. But of course, we have a number of PI teams, 11 something on the orbiter, 10 on the lander, and that are the interfaces also with other groups involved in the science planning. And for all those interactions to work, I need to follow what they do and try to spot things which could block progress, and try to make sure that all the elements are there. One of the things that Andrea mentioned, of course, is that it's already difficult enough flying at the Comet, assuming we know what it's like. But the big thing is, we don't know what it's like. So in science planning, for example, we take multiple approaches. We have a low activity planning and a high activity planning going on in parallel. On top of that, there are uncertainties which are quite natural as to the landing. We have a nominal date, but it could be that through whatever, we have to go for a backup landing site, and that delays everything and throws everything in the air again. So at the moment, from the science planning side of things, there are at least 5-6 different threads running in parallel. The planning of the operations just before we are at the Comet, the long-term planning of operations after that, etc. And I'm just trying to make sure that everybody can do their job. And of course, in a project like this, where there is a lot of work, you also have a lot of stress, because people make very long working days. And well, not surprisingly, a big fraction of my work is to make sure that people keep on communicating efficiently while under such immense stress.
Fred, I wonder if you could give us a little bit of a flavor, a little bit of the sense of the international scope, the number of countries or the number of institutes that are working on the science side of Rosetta.
It would be difficult to estimate the number of institutes, but it's basically all the member states of ESA are there. And then there is, of course, large contributions from NASA, and so effectively you're talking about something like 13, 15 countries and at least something like 40, 50 different institutes throughout the world, Europe and the US being involved in this. And if you think about number of people, to give an idea, there are some 30 people at ESAHangout, some 30 at ESAC, and then in the PI teams on the orbiter, I would estimate together at the moment something of 100 in Europe, and there must be another 25, 30 at least in the US. And that's then the orbiter part. On the lander side, there is Cologne, Toulouse, CNES, and the PI is there, and I think that together is also somewhere between 40, 50 people at least at the moment. So it's a very large number of people fully dedicated to this mission.
Great. Fred, actually, one more question I wanted to toss your way is just yesterday we had an update in our Rosetta blog showing an animation of some of the NavCam images. Could you explain a little bit about where those images came from and how they're actually being used?
Well, the images are from the navigation camera, the NavCam that Andrea already mentioned, which is the thing we will be using to navigate and point at the comet using the landmarks that we will establish early August. This NavCam at the moment is used to determine where we are relative to the comet. It's being used together with images from the OSIRIS camera, but we're now getting close enough such that the NavCam can do it on its own. And this camera has been taking images multiple times a day from the 8th of May onwards. And what was yesterday released was basically a daily image of the NavCam in some very poor amateur way put together in a movie by me, unfortunately. That's why it's amateur. And released for the public to see Rosetta, or basically the comet, moving with respect to the sky background, the stars.
Great. Yes, I know. Talking to the flight dynamics guys here at ESAH, they're using those images in an integral way to help to locate the position of the comet and plan some of the burns. You mentioned actually NASA, and I thought a quick question back to Andrea. Could you give us a little bit of an overview on how we're cooperating with NASA? I know we're working with the ground stations and some other areas to work the mission.
Yes, the collaboration with NASA is there since the very beginning on Rosetta. It's an international mission, so it's a collaboration between ESA and NASA. NASA are providing two instruments, full instruments on board the spacecraft, and some other parts of other instruments. In exchange, they're providing also some services to us. Namely, they provide ground station support, so we use their antennas to communicate with our spacecraft, and this is a very precious resource. They complement very well with our network of antennas. They also have resources that we do not have, very large dishes, larger than ours. In some specific operations, we needed these resources, so this was baseline since the very beginning of the mission. On top of this, we have a very tight collaboration with the navigation colleagues in JPL, in the Jet Propulsion Lab, and they are doing a parallel, let's say, activity to some of the activities we are doing here in flight dynamics. And this is done for two purposes. First, we exploit together this unique opportunity of this fantastic mission and this challenging operation to develop in each respective center the capability to conduct these operations, but it also is a sort of insurance that we are doing proper job, so we can cross-check continuously with them that the data are consistent. And this is, of course, enhances dramatically the reliability of the mission itself, and this is a marvelous sign of cooperation in my view.
Good stuff. Actually, speaking of NASA, maybe, or the U.S., maybe this is a good time to segue over to our guest from the U.S., Padma. If you're still awake, I know it's sometime before 5 a.m. in the morning there. I wonder if you could give us an overview, in general terms, of what's happening with the ground observation campaign and some of the results that you have seen or that you're hoping to see, looking at 67P from a number of different countries. And it could be that your mic is on mute.
All right, can you hear me?
No, I think.
No.
Oh, there you go. Yep. Yeah, there you go. That's good. Now we've got you.
Okay, can you hear me? Hello?
No, I think.
Yeah, Padma, I can hear you at least.
Yes, that's perfect. Exactly.
Okay, great. All right. Well, thank you, Daniel, for that introduction. You know, what I love about this mission is it's doing very interesting and challenging engineering tasks of actually going to a comet, but also it's going to land both lander as well as be in orbit for the next so many months. And so one would think that that's all that we need to do, but the ground-based observers provide a complementary view from what the Rosetta mission does. That is, we provide a global view of the environment of the comet and its activity, versus the local view that you get from the orbiter instruments and the in situ view that you get from the lander. So there is a role that the ground-based observers play. And also, the ground-based observers are of two communities: the professional observers that have access to a lot of the instruments and the large telescopes around the world in the and explored in the electromagnetic spectrum, and the amateur community that basically observes in the optical wavelength, but they're also spread globally, and they provide a bridge between a lot of different science questions that the professionals on the ground-based telescopes and on the mission have. And so there is a need for each community to provide what they can in terms of support for this fantastic mission. And so coming specifically to 67P, it's a faint target, and it's just been recovered as of January that the ground-based telescopes have been able to observe it. The professionals started acquiring it in February, at least, that I know of. And then the amateurs have just recently started being able to find the comet, but it's in such a dense star field, sometimes it's hard to track it. But yes, we have been having some success with amateurs with as a smaller telescope as I think 12 inches to 14 inches. And so this is very exciting because the amateurs basically can provide a temporal baseline against which one can then place both the mission as well as the professional observations in context in terms of when they need support or any other activity that we can observe that the spacecraft isn't seeing at that moment. And so there is a natural fit here.
Great. Can you give us an overview on how many countries are participating, or people in how many countries are participating?
Well,
I know Australia is a very big...
Yes. Well, right now the Comet is available at the southern latitudes, and so the aim is to have a global network of amateur astronomers, and we're working towards that goal, and we actually are doing very well. But since the Comet is available only in the southern hemisphere, we've had lots of amateur astronomers trying from Australia. We are also having some people are in South America and South Africa. So as when if the comet comes to the point where it can be seen in amateur telescopes, we're going to have our network of amateur astronomers around these countries trying to observe the comet. Now, the northern hemisphere, at the northern latitudes, many of the observers can't see it yet. So as the comet traverses its orbit and it becomes available early next year, we'll have northern latitude observers also be able to observe it, and in the southern hemisphere they'll start losing the visibility. So eventually we're going to try to get as many observers around the world to participate, and we take advantage, the amateur astronomy community at least takes advantage of all the social media channels. These weren't available a few years back, but thanks to Facebook and Pinterest, Flickr, Twitter, we find that the amateur community rapidly corresponds and shares their images. And so we're trying to take advantage of all of this to be able to have a continuous monitoring of the comet. And I think that's an exciting new way to look at a mission.
Okay, just one technical question for those of us who are not astronomers. Will ground observations be able to resolve the comet at all in the next 6 months, or how big of an object will we be able to make out?
I think there'll be a little bit of success with the larger telescopes, the 8-meter telescopes. For the amateurs with the smaller scopes, they won't be able to resolve it, but also it may at best be a binocular object, but the comet is supposed to faint in this apparition. It comes around every 6.5 years, and so compared to the previous apparitions, this one is supposed to be a little fainter. Also, its orbit is such that it gets closer to the sun, and at a point where we need, as it's getting close to perihelion, and so we basically, you may not be able to resolve it, but you can actually still get a lot of science from what we observe, and also the fact that it interleaves with the professional observations. The professionals will be able to say, I think they'll be able to get a lot more spatial as well as spectral resolution than the amateurs will.
Great, thank you very much. I'm seeing a number of questions coming in via Twitter and in the Google channel, and I think maybe we could start looking at some of those. And the first one I'm looking at is from Antonio Garcia. He's asking, I think this is for you, Andrea, are the landmarks that you mentioned on the comet, are they going to be established using automatic methods or algorithms, or is it done manually by eyeballs?
Well, this is the first time we do anything like that. So we have developed a software to help us or to do it automatically. But in the very beginning, we will start the process definitely manually. This is because we want to test. This is a first experience. Of course, we have done our testing. But definitely, we are capable of running the process in both modes. And this is what we do. We will definitely start manually. And after a while, if the automatic method proves to be reliable, then we will use it.
Great. And I see a question coming from Jonathan Klump. He's actually teaching 17-year-old students, so that's high school. And he's curious about the thrust and delta V of the recent burns, and also curious about the percentage of error on the mission calculations. And this is in reference to our current sequence of 10 orbit correction maneuvers.
Okay, as I said during my previous intervention, we had a relative speed to the comet of roughly speaking 800 meters per second, a bit below that. But with the big maneuvers we have already done, we have almost canceled almost all of it. We are left with a bit more than 100 meters per second. And this is what we are going to, in the next maneuvers we do, we remove another 60 meters per second. And the next one is 25 meters per second. Then the relative velocity of the two objects will be very, very small. This is what we are doing. We're doing these maneuvers with very small thruster. The spacecraft is still, well, heavier than a ton. It's in the order of 2 tons right now, the spacecraft. So it's relatively heavy, and the thrusters are very small. So these burns are very, very long. The ones we have completed so far, the longest were more than 7 hours continuous thrusting, or 4 thrusters, and they are firing currently in the order of 5 to 6, 7 Newton each thruster. So the thrust we get is very, very low.
Right. Now, correct me if I'm wrong. Those 3 initial burns, the 3 after the first burn number 2, 3, and 4, they were some of the biggest burns ESA has ever done in terms of a spacecraft running its thrusters for almost 8 hours.
Well, definitely in terms of duration, absolutely. In terms of delta V, a change of velocity, I can remember the one of Venus Express reaching Venus when we had the orbit insertion. This was 1,300 meters per second in a single burn, but with a much, much bigger engine. It was only 40 or 50 minutes burn.
Right. These are thrusters. Right. Another question, which actually is a very timely question, and it's coming in from Zuzana Kovic. She says, do we have any idea why the comet's activity has declined over the past few days? What is the effect of the comet activity on the mission success? And Fred, I wonder if you want to address that one?
Well, yeah, as we, to start with the first part, as was released earlier in an Osiris sequence of images towards the end of April, we saw an increase in activity of the comet, which, as we said in a recent release, has died down again. But this was a bit unexpected. On the other hand, it tells us it's a comet, and it's active, and it will do this continuously. And that's what's difficult about this mission. I mean, it's difficult enough getting there and flying around an almost gravity-free object, but then this thing throwing balls at you all the time with 40, 50 kilos of ice is a very complex thing.
Right, and Padma, I'm wondering, has anyone on the ground been able to actually track or get an indication of the comet's coma, or the degree of activity with the coma, looking at it from Earth? Actually,
no, and yes and no. We have members who have indicated that they have detected the comet and shared some images with us. And we wrote a blog about that, and following the blog, we found out that other folks had also been observing the comet as early as March, I believe. I'm not sure if I can share my screen. I can show you a couple of those images, but Peter Lake, on May 22nd, from using a robotic telescope network in Australia, was the first one that we wrote a blog about. The magnitude was 21 magnitude, I believe. It's rather faint. And the challenge is basically that the comet is moving slow enough, but it's in a very crowded star field, and so sometimes it's not easy to spot it. So if I could share my screen, I don't know if you can see it. Can you see the screen?
No, we're still seeing you right now.
Oh, okay. I'm not sure I know how to share the screen then. Well, while I figured that out, but yes, we as recently as last night, another observer from Puerto Rico said that he actually was able to image what he thought was the comet, and again, it was in a very crowded star field, but it was close to several bright stars, so the magnitude seems to have increased a bit, but because it's so far, it's a faint object for us. For the amateurs, that is, we still cannot distinguish any kind of activity or coma around it. I haven't heard anything from the professionals, but the coordinator for the professional observations, Colin Snodgrass, is traveling, so I don't know the most recent results from the professional observations. But I guess, like Fred indicated, that the earlier activity was related to an outburst, and essentially the comet has quietened since then. What I'm impressed with is the fact that now that the smaller scopes are starting to pick up the comet, and so starting from maybe in a few months, we may be able to start seeing more structure or activity around the comet.
Great, thank you. There's a question coming in also again from Antonio Garcia. And he's saying, as regards to cameras, I think this is for Fred and Andrea. Rosetta is equipped with OSIRIS, of course, that's the main optical instrument, and Philae with ROLIS. And his question is, will they be working together at the time of landing, or would it only be the ROLIS camera, for example? And are these devices capable of taking video? And I would add in the follow-on question is, will Rosetta be able to get shots of the lander landing?
Okay, there are several questions here. We have more cameras, actually. We also have the navigation camera, which was already mentioned, and the lander is also equipped with a panoramic camera. It's called Shiva. So all these cameras can take images. They cannot take videos. We can reconstruct or build videos on ground, but on board, the files are single images. Operating together, well, this is up to us. We downlink the images, all of the images on ground, and some teams have access to multiple images or multiple sources for these images. Some teams only on one camera, so it depends. For sure, we will try to use them as much as we can. I can quote already that now for the navigation, for approaching the comet, we at ESOC, for the navigation purposes, we are using NavCam images, our navigation camera, and OSIRIS images. When we get to the comet, OSIRIS has actually two cameras, a wide-angle camera and narrow-angle camera. When we get to the comet, we'll use also the wide-angle camera of OSIRIS for our own purposes. So we combine all the sources together, definitely. I don't know, Fred, if you want to add anything.
No, I'd just like to say that the landing itself, yes, we will make an attempt after the separation to look at the lander, and the lander will look back at Rosetta. And then at the time of landing, there is a combination of SIVA and ROLIS, which will be used to establish that we are on the comet, and that, for example, the legs of the lander have screwed in to the surface before we fire the harpoons. So especially around the landing, there is a whole interplay of all this imaging to make sure we know where the lander is, and that if the lander is on the surface, that we know that it has attached itself.
Right. Thomas Oriel asks a question, why did you put Rosetta into hibernation? Was it something to do with the power from the solar panels?
Absolutely correct. This was baseline since the very beginning of the mission. I acknowledge the fact that it's an extremely brave decision, was a major technical and psychological challenge as well to put Rosetta in hibernation. We analyzed and challenged this design feature since the very beginning, since the late 90s. I was involved in this, but there was no chance. There was no chance to have flying Rosetta in a safe and reliable way, fully active at the distances to the sun we have been. So the less risky option was to hibernate Rosetta, because the power generated by the solar rays was not enough simply to keep the spacecraft in an operational mode. So that's why we had to hibernate it.
Right. And again, I think another question for Andrea. How do you communicate with Rosetta? What is the operating system that is used in Rosetta? And how long do you have to wait before you get an answer back from the spacecraft?
Okay, well, the communications are established to a radio frequency link. We have two bands on board, the radio frequency band at 2 gigahertz, Sierra band, S-band, or X-ray band around 8 gigahertz. This last one is the prime used for communication. The other one is either for radio science purposes or for scientific investigation or for backup modes. The communication occurred through big dishes, big antennas on ground, and then they established the communication with the spacecraft. The operating system, Rosetta, as an operating system that is a real-time system. You cannot imagine as your own PC, as a computer working in real time permanently. There's of course no graphical interface, and there is this software that was as an interface with our ground systems. We can send instructions to Rosetta to take actions, and we receive data back, which is what we call telemetry. This is what it is.
Okay. And our one-way light time typically
yes, right. Today is in the order of 24 minutes today. So 24 minutes to go to the Rosetta and come back. The day of landing will be, the Earth will be farther away, is in the order of 30 minutes.
Good. And actually, I think this one, Fred, is probably for you. It's asked by Nick Howes in the UK, and he's wondering about the contingency plan if the comet goes into a more significant outburst when the spacecraft is nearby. Or when Philae is deployed, what do we how do we handle that? I think your mic may be muted.
Yes, sorry for that, Daniel. There are two things here.
No problem.
The comet can have such an outburst that the spacecraft ends up in what we call safe mode, and then our procedures say we immediately basically go further away from the comet. That's the emergency situation. When we are normally flying at the comet, you have to imagine that the comet, which we navigate on, is rather close to Rosetta. But the comet pushes away Rosetta. So at some stage, our camera, because we are at a different point in space than we want it to be, no longer sees enough of the comet to be able to navigate. If that happens, we also have a plan, but then actively we steer further away from the comet to allow ourselves to operate. So these are basically the plans we have to deal with variations in cometary activity. And as I said, we continuously prepare for a low activity case and a high activity case science scenario.
Do you want to add anything to that? Or?
No.
Yep. Okay. Good. Okay. There's another question coming in, and it's asking generally what type of imagery can we expect at rendezvous time? Can we expect some images? At what rate? Thanks and congratulations. That's coming in from Eduardo Lateo. So I wonder, Fred, would you like to respond to that on just what will we be able to see around rendezvous on the 6th?
Yeah. Well, there is a subtlety here, of course, that we have said. We have a plethora of cameras, and we will have lots of imagery. What you have to bear in mind, though, is that it's a science mission on which people, a large number of people, have invested a significant amount of time, between 10 and 20 years for a large number of the scientists involved. So not all the images will immediately become public, because there are scientific investigations which have to be done, and for that they have what we call a proprietary period, which is standard on all these science missions. So we will release a number of selected images showing the comet, of course, and what we do. But we cannot put all the images in one go on the market.
Right. There's another question which we've mentioned about, Fred, you've mentioned about the activity at the Comet and how that does affect our spacecraft. The question is from Thomas Oriel. He writes, if I remember correctly, Giotto had some problem when it crossed the Halley's Comet tail. How will Rosetta manage that? And how does that compare to what happened with Giotto?
Well, Andrea probably knows the hard numbers better than I do, but he already gave away part of the clue. The clue is that Rosetta is flying very slow with respect to the Comet, where Halley flew by off the top of my head with something like 40 kilometers a second. And we are approaching Rosetta with walking speed, a few meters a second at most. And that's why the dust that impinged Halley and was the problem with Halley is much less of a problem for Rosetta, because the energy of a particle goes with the square of the velocity. So if you talk about 40,000 meters per second and Rosetta at 1 meter per second, the effect, a quick calculation learns me, is something like 16 times 10 to the 8 stronger on Giotto than it is on Rosetta.
Okay. There's a question coming in from Jonathan Amos, whom I believe is located in the UK, and he says, is there any evidence of 67P spinning up or spinning down as a result of the observed recent activity? And I wonder if you've heard anything from the...
Well, I'm afraid I'm not in a position to answer. First, because I'm not a scientist and I'm not processing the science data. I'm pretty sure the scientists are looking at these data, but I have no evidence or no news about this. I don't know, Fred, if you know anything.
I know that they have detected the rotational velocity of the comet, and that they're comparing this with earlier ground measurements. And this is an ongoing activity, and part of this will probably be presented next week in a meeting on comets and meteors in Finland.
I think the interesting point there is that actually what we are doing here in characterizing the comet, it is very much a real-time activity. It's something that we're finding out as we go, and that's what makes this mission exciting.
Well, Daniel, the crucial point here, of course, is you have to separate. We're doing science from flying the Rosetta, and what Andrea is doing, he does what is needed to fly Rosetta around the comet and deliver the lander. And we do that totally separated from the science to be able to not get in each other's way.
Right. There's another question coming in from Ian Constantine, and I think this is for you, Padma. He's asking, when is perihelion for the comet, and is it expected to be naked eye visible at any point as it's approaching the sun? Oh, I think you're muted again, Padma.
Okay. The comet is expected to reach perihelion on August 15, 2015.
No, yeah, that's better, yep.
About a year from now. And it will not be a naked eye object. Its estimated magnitude is about 12 to 13. So it may just be at the limit of binoculars, but it'll be definitely a telescope object.
Okay, so it's actually not going to be naked eye visible, right?
No, it will not.
There's a question. Okay, thank you. There's a question coming in from Peter Lake. He's actually asked it twice, so I think he's rather keen to ask. He's referring to the rather extraordinarily long duration of this mission. It's more than a decade, and he's wondering, how do we maintain continuity of skills and succession planning? And that could refer to the operations team, it could refer to the scientists. Maybe both Fred and Andrea could respond to that.
Well, I can quote personal experience. I started working on this mission in '96, so this is continuity. I have been there for the last 18 years of my life, but I'm not the only one, of course. Though you have to plan. It's an absolutely valid point and raised many concerns on our side, mainly on our side as operators. We had to be ready for launch in 2004 and to be sure to be there again now in 2014. So we had carefully planned turnover of people, turnaround of people going and coming, and we managed pretty successfully to have a core team today that still has some knowledge of the original team of Rosetta. It's my case. Other people were originally in the team, not all of them, but this is something that has been managed properly. similar problems on the scientists. Maybe it's even worse. So this mission was conceived in the middle of the 80s, then started implementing middle of the 90s. And I don't know, Fred, if you know anything more on this.
Well, what I can say is that from a management perspective, yeah, we rely on people like Andrea, of course, and in the project and in the institutes, in the science institutes, to be there. I myself work also on another project where I've been 26 years. So it's crucial that people like this exist. On the other hand, what we have done on Rosetta specifically is close towards launch, we have videoed the people who designed crucial parts of Rosetta, and we have digitized these videotapes and indexed them. And they basically tell how they designed the instruments and Rosetta and how it was supposed to work. So in case we really get stuck, we can go back to these videos and listen to the people who told us what they intended to do at the time.
Right. There's a question coming in from Deirdre Kellican. She is asking, do you have any idea what the shape of the comet is, and why did you choose 67P? Is it large enough to survive its visit around the sun? That's maybe a question for almost any of you. Maybe Fred, why was 67P chosen?
Well, 67P wasn't chosen, and that was part of our problem. The original Comet was a different one. And when we came close to launch, there was a problem at the time with Ariane. And we couldn't launch at the point in time when we needed for the original Comet. So a new Comet was found, but it's much lighter and smaller than the original Comet. So actually, things like the lander suffer a bit from this, and we have to work around a number of things. So that's in a nutshell how we selected this Comet.
Padma, do we expect this comet to actually survive? Just recently we had Comet ISON doing its loop around the sun, and it kind of disappeared. What's our crystal ball forecast for 67P?
Well, 67P is a periodic comet, so it has an orbital period of 6.5 years. So every 6 to 7 years, we have at least seen it 7 times before. And so I don't see any reason why we won't see it again. The last apparition was in 2009, and so since 1962, I believe it's come about 8 times. So I think yes, there's a high probability it'll survive, unlike ISON. But each apparition is a little different, and so how it will be on this next passage. That's to be TBD, to be determined when it happens to come by again.
Okay. And on the question asking about, yeah, go ahead. Yeah, Fred.
There was a question you had. That was part of the question I forgot to answer, which is about the shape of the comet.
Exactly.
What we currently know about the shape of the comet is from light curve measurements done by Hubble, and there is a so-called Lamy model, which basically interprets that light curve and made a comet shape out of it. Evidently, one of the first things we look at to do with Rosetta is to revisit that with more up and close measurements.
Right. I'm looking at the next question here, and it is coming in from. I think this is for you, Fred. It's asking, why don't we see any changes in the trajectory during the last burn in the video? Shouldn't it be visible in the nav cam? And I think that's in reference to our NavCam animation published just yesterday.
Well, it's a bit complex, but yes, if you look purely at the speed of Rosetta with respect to the comet, you would say, yes, we are much slower, as Andrea already said. So the sky should move much slower behind Rosetta. However, at the same time, we're coming much closer. And the movement of the sky is a projection effect because the NavCam is pointed towards the comet. So it's a combination of getting closer and slowing down, which keeps the sky roughly at a constant rate per day, in degrees per day, that it moves with respect to Rosetta, Comet, and the sky.
Right. Okay. Good. We're looking here at a couple more questions. There are a few more coming in here. This is one coming from Elisabetta Bonora. She says, under what light conditions can Philae's CCD work? I wonder how will be the landscape, how will be the with respect to light refraction, opacity, and shadows. Do we have an idea, any forecasts on what Philae sees on the surface?
Well, no, I definitely not entitled. Maybe Fred knows.
Maybe Fred knows. Yeah,
more experience.
I know a bit more. These instruments are made to work in a variety of light conditions, and so the exposure time will actually be commanded or set rather shortly before the actual landing, such that we know more about the density. In general, it is one of the big unknowns. The lander has two elements. It works on batteries the first 60-something hours. After that, it has to recharge its battery from a solar array. And how much science we can do after the initial sequence actually depends on how much sunlight there will be on these solar arrays. That depends on the amount of dust, gas in the atmosphere, but also how much crud basically settled on top of the solar arrays during the landing. So there is a significant number of unknowns there, yes.
Right. There's a question coming from Adrian Newsom, and he's asking, are you going to leave Rosetta on the Comet or at the Comet? Simply leave it recording data as the Comet goes nearer to the Sun, and then finally back out away from the Sun again. So basically asking what becomes of Rosetta and the lander in the future?
Well, definitely there's no energy enough on board Rosetta, so chemical propulsion to move Rosetta away, farther away from the Comet orbit. So we'll be forever either around the Comet or maybe on the Comet. I don't know yet. We will see with Fred. We will decide in the coming years what to do. But definitely, it's not a mission that can go far away from that Comet, definitely. So it will remain forever there.
Fred, do you want to add anything to that?
No, Andrea said it all.
Right, okay.
Well, one thing, an important thing to realize about Rosetta is that, of course, we're all highly excited about the landing happening in November. But after that, the science of Rosetta continues, and actually a lot of the science of Rosetta continues, flying along with the Comet until, well, somewhere in 2016, when we, as Andrea says, we will run out of steam. And a very large fraction of the overall Rosetta science will be done by the orbiter. So we have to keep this into perspective.
So basically what you're saying is we're getting a lot of the science benefit once we've arrived at the Comet, and our spacecraft is following the Comet as it arcs around the Sun. That's our...
that's the mission.
That's our mission.
Yes.
Right. This question coming in from Maulana Mormar. I'm sorry, I'm not pronouncing that very well. He's saying, what will you do after you put down the Philae lander on the Comet, and what is your next destination? Seems like a rather general question.
Shall I give it a go?
Sure. Yeah.
Well, as I said, the Philae lander has an autonomous science sequence for the first 60 hours, which it will execute. After that, it will recharge the batteries, and we expect that we can operate something like 1 hour every 48 hours. This will probably continue for another month, after which the lander will be inoperable, most likely. And Rosetta, as I say, flies along the Comet, but what it does actually, it flies on specially designed trajectories, which sometimes come close to the Comet, sometimes go further away, and we do all kinds of campaigns in those special roller coaster-like orbits around the Comet.
Right. We're coming towards the end of our ESA Hangout, and I'd like to ask each of our guests to give a quick, just a couple of minute summary, what you're looking forward to in the next couple of weeks, next few weeks, what's coming up on your schedules, and what you're looking forward to. Padma, we could start with you. What's coming up in the next little while?
Let's see. I'm going to see if I can do a quick screen share because what I want to say is in the next few weeks to months, we will be. I'm trying to figure out how to. Okay.
Yep, it's there.
Let me see. Okay. I have multiple screens showing up on mine. I don't know how it looks for you folks.
If you screen share the video, it goes into a recursive loop.
Oh gosh. Okay. How do I? Okay. I was just trying to show some images from the amateur astronomers that have been shared recently, and I think as time I'm trying to stop the screen share, but okay. Well, sorry, I couldn't get that graphic up. But as time goes on for this mission for the next year, 15, 18 months, the amateurs are going to be able to do a lot more imaging of the comet, so that we can actually also feed into science questions like basically the light curve of the comet, also any other activity features that come out, outbursts. And so the fact that the amateurs can now pick it up in a smaller scope is very exciting. Some of the amateurs can actually do a spectroscopy, so trying to understand the chemical species that you see in the coma and further in the environment of the comet. Those are going to be very exciting advances. And so we're looking forward to all of that, and as well as our collaboration with the scientists, depending on how and where they need support when they're observing or when they're not observing. And so we have an army of amateur astronomers willing to help, as well as on standby, so to speak, on a moment's notice. So that's a very exciting aspect of this campaign.
Great. Andrea, I'll pass to you. What's coming up in the next few weeks that's keeping you busy?
As I said, we have entered now the final approach phase to the comet. For me personally, what I'm really looking forward to seeing is what will happen in August. On the last weeks in July, last days in July, when we really get there to the object, we characterize the object. We have to do this in a very short period of time. This is a major challenge. Once we have done this, then we are in a position to really fly around the comet. I'm really looking forward to see this happening. Is the first step to do. There's much more to do beyond that. The first one to come up is the global characterization to be able to land onto the comet, something that has never been attempted. And as Fred say, much more to come afterwards. But the first step for me, the month of August, what we'll do in August is really the key for the rest of the mission. Is we rendezvous, we characterize, and we orbit the comet. This is what I want to see now.
Great. And Fred, over to you. And actually, I'll toss out to you one of the most interesting questions that came in from Chris J. And he said, "What do you hope future Earthlings would say that Rosetta's main achievement was?"
Let me answer in a philosophical way. If future Earthlings know about Rosetta and remember it, I think we've done a good job. Because this is not trivial to get your place in history. To speculate about what I would like to see most would be saying that if I don't find that, I would be disappointed. But evidently some of the primary science objectives, larger molecules which could be building blocks of complex chemicals which eventually could make up life, are things we are really looking forward to. And I think that would definitely make its mark into the history books.
Great. That is pretty much a good note to finish up today. I'd certainly like to thank our guests, Fred Jansen, Mission Manager for Rosetta at ESTEC, Andrea Accomazzo, Flight Director here at ESAHC, and Padma Yanamandra-Fisher over at JPL. Thank you very much for joining us today.
You're welcome.
Thank you.
And for our audience, the archive copy of this ESAHangout will be available here in the Google Plus channel. It will also be available under youtube.com/ESA, and we look forward to sharing future ESAHangouts with you again on Rosetta, on other ESA topics, and of course here at ESA we're celebrating our 50 years of European cooperation and innovation, so we have a lot of cool stuff happening. You can follow Rosetta mission progress via our main website, ESA.int. You can also follow via social media, which you can find all of our social media channels under ESA.int/connect-with-us. And we look forward to seeing you at the next Hangout. Thank you very much for joining today. I'm Daniel Scuka, and thank you.